Hello guys, I feel like it's been a billion years since the last time we had one of these videos. I'm sorry. I was really sick for a while and that's one of the reasons, and I also didn't have time. I was working on other things. So anyway, um, let's work through the October 2025 paper. Okay, it's the most recent one I was able to find, and this is unit 4. Okay, and I've seen that there is a version called Unit 4A, so where it says WPH 14/01, it says 01A. Okay, so there is a version like that. I don't know why there are two versions from 2025. If you guys know anything about this, let me know in the comments. But anyway, let's jump right in with section A. Again, I think I say this in every video, but usually the rule of thumb is if a question worth 1 mark, it means that it should take you about a minute. So all of the questions in section A should take you about 10 minutes, but okay, if they take you 15, that's fine. It's not the end of the world. So question 1. Which of the following shows the electric field around a proton? So a proton is positively charged, okay? Therefore, the electric field points outwards, right? So it's immediately A, okay? And we can immediately eliminate in this case, I don't know, I'm working with GoodNotes and they keep changing the menu, so I cannot find the colors and the pens and all this that I'm looking to find. That's why it takes me time to respond sometimes. So anyway, for 1, it's A. You can immediately eliminate C and D because these are equipotential surfaces. They have nothing to do with electric fields. So again, in section A, sometimes you can eliminate answers just by looking at what they state. So let's go to question number 2. In the sun, 2 protons can combine to form a proton, a neutron, and another particle X. Which of the following particles could be X? So first of all, it cannot be a baryon because the baryon number is 2 for 2 protons, and then in the right hand side we have a proton and a neutron that also have a baryon number of 2. Therefore we know that this is not a baryon. The baryon number of this thing called X is 0. Okay, and also the charge is 2 for the 2 protons, and for the proton and neutron the charge is 1. So we immediately know that the charge of this X particle is 1. Okay, so it cannot be a baryon, so we eliminate the baryons. It cannot be a negatively charged meson because we will not conserve charge. So it can only be a positively charged meson, okay? Because we need to conserve charge and baryon number. So let's move on. Question 3. An alpha particle passes through a small thickness of absorber. The momentum of the alpha particle is halved. The initial kinetic energy of the alpha particle is E. Which of the following is the kinetic energy of the alpha particle after passing through the absorber? Okay, so the initial kinetic energy is simply p squared over 2m. After it passes through the absorber, let's call it kinetic energy prime. It's going to be p prime squared over 2m, but p prime is p over 2, so we get p squared over 4, and then we still have this 1 over 2m. So immediately see that it's 1/4 of the initial kinetic energy. Easy, right? So B. Right. Question 4. Which of the following is a scalar quantity? So A, capacitance, that works. Capacitance is a quantity. I mean, it's a scalar quantity. It doesn't have a direction, right? And everything else you can check has a direction. So the acceleration, impulse, momentum, and so on. Let's go to question 5. Muons are unstable particles. At speeds approaching the speed of light, relativistic effects change the lifetime and the rate of decay of the muons. Which row of the table is correct for these muons? So at relativistic speeds, we have time dilation. Therefore, the lifetime, let's call it T prime, increases, right? But remember that the radioactive decay law, and especially the rate of decay, which is A, right, goes like A naught e to the minus t over t prime. So if t prime increases, then the rate decreases, right? And the answer is C, right? Yes. Okay, which makes sense. If the lifetime increases, we will have a smaller number of decays, right? So, okay, let's move on to question number 6. Okay, this was a little bit tricky and I got fooled in the beginning, but then I found my mistake. So we have two circuits, J and K, each contain a coil, okay? When the AC supply is switched on, an EMF is induced across the coil in circuit K. Which of the following would increase the magnitude of the induced EMF? Okay, increasing the distance between the coils will reduce the induced EMF because we will have less magnetic field lines passing through K, so that's not correct. B, increasing the frequency of the AC supply. That sounds promising, and the reason is that EMF is given by minus dB times A over dt, and then we have an N up front for the number of coils. Okay, so if we increase the frequency of, okay, so this B over here, okay, is generated by circuit J, right? Because if we have a current passing through this circuit, we have an induced B, and that induced B induces a current circuit K, okay? So if we increase the frequency of the supply, the frequency with which dB over dt changes increases. Therefore, we have a stronger EMF in circuit K. Okay, so the answer is B. Originally, I answered C, but C is wrong because if we decrease the number of turns in the coil in circuit K, we will decrease the induced EMF. Okay. Okay, so let's move to question number 7. The nucleus of carbon-11 decays by releasing a positron E+. Which of the tables shows the proton number and nucleon number of the nucleus produced? So, because it releases a positron, we know that we have a beta plus decay in which a proton, a positively charged proton decays into a positron plus a neutron plus an electron neutrino to preserve the lepton number, okay? So we will have carbon 6 emitting, let's call it beta plus, okay? 0 plus 1. Therefore, we will have a nucleus with the same number of protons and neutrons, but that's boron, right? Because we will have one proton transforming into a neutron. Therefore, the proton number will be 5, and we also have an associated electron neutrino emitted. So the correct answer is A, right? And this nucleus carbon-11 is very useful in PET scans, okay? For those of you who want to go a little bit deeper into questions. So PET scans use carbon-11 because I think its lifetime, it's about 10 minutes, maybe 20 minutes, something like that. So it's perfect for doing PET scans. So let's move to question 8. In a cyclotron, charged particles are accelerated to high speeds by applying an alternating potential difference between the two Ds. The alternating potential difference must have a particular frequency for the particles to be accelerated each time they cross between the Ds. Which of the following statements is not correct? Okay, first of all, when we have circular motion, actually let me create a clean page, okay? So this is question 8. Okay, so mv squared over r is qvb, okay? So I'm talking about particles, charged particles in the Ds, okay? So you have an alternating AC current between the Ds, okay? So this is the other D. And in here, the particle undergoes circular motion, okay? and that the R that I wrote there is this R, okay? So let's eliminate V, and you will see where I'm going with this. So we have M times V is QB, but for circular motion, recall that V is omega times R, and this is QB. So omega is QB over MR. Something bothers me over here. Oh, I forgot to carry the R. Okay, so there is an R over there, so this R cancels. So let's erase this R. Okay, and recall that omega is 2 pi times the frequency. So the frequency is pretty much QB over 2 pi M. So it depends on charge. Sorry, this should be M. It's been a while, guys. I'm a little bit rusty. Okay. So the frequency depends on the charge of the particle, the magnetic field, and the mass of the particle. I'm sorry. So the only answer that is wrong is D. The frequency does not depend on the velocity of the particle. All right, question 9. A ball of mass m falls to the ground and rebounds as shown. Okay, the speed of the ball just before colliding with the ground is v. The speed of the ball as it rebounds from the ground is v over 2. The time taken for the collision is delta t. Which row of the table is correct for the mean force acting on the ground during the collision? So they are asking us for the force on the ground, okay? Not the ball. Okay, that's a trick. So to solve this kind of problems, you take a direction. It doesn't matter which one. So you take this direction. Let's take the upwards direction as positive, okay? And let's find delta p. Okay, I'm going to use this clean page. Okay, so let's find delta p for the ball. Delta p is going to be m times v final minus m times v initial. But v final is upwards, so we take it as v over 2 minus m times v initial, but v initial is down, right? Whereas we take the upwards direction as positive, so we need a minus sign to account for that, so minus v. So delta p is 3 mv over 2, right? And now f times delta t is going to be 3 mv over 2, which is delta p, right? So f is 3 mv over 2 delta t, and it's upwards, but this is on the ball. Therefore, for the ground, f ground is minus 3 mv over 2 delta t. Okay, so the correct answer is C. Okay, and last but not least, by the way, this was a difficult test, I have to say. Okay, when I was going through it, I felt like it was hard. It was an easy one. Okay, too many questions and too much work needed, even for these simple ones. I mean, the supposedly simple questions. Okay, a particle moves at constant speed in a circle. P and Q are two positions of the particle. The velocity at P is Vp and the velocity at Q is Vq as shown. As the particle moves from P to Q, the change in velocity is delta V. Which of the following is a correct vector diagram for the change in velocity of the particle? Okay, so delta V is going to be Vq minus Vp, right? So we can write this as Vq plus minus Vp equals to delta V. So let's go check these diagrams and see. Okay, first of all, A is wrong because it tells you that Vq plus delta V is Vp, so that's wrong. Then Vp, if we go to B, we see that it tells us that Vp plus delta V is equal to minus Vq, so that's wrong. C tells us that Vp plus delta V is Vq. That sounds promising. Is it promising? So if we bring the Vp plus delta V is Vq, okay, that looks promising, but let's see. Okay, delta V cannot point upwards. Okay, so C is problematic. Let's go and see D. So we have Vq plus the negative of Vp equals to delta V. So that's correct. But now I'm a little bit confused why. Okay, the way C is written, it can also be interpreted as saying that Vq plus Vp equals delta V. So no, that's wrong too. Okay, so I found the error. Okay, so this was part A. I tried to go a little bit fast because I want to finish this a little bit fast today. Okay, so let's do section B. Okay, let's start with question 11. It's 2 marks. Okay, again, this indicates that it should be an easy question. Okay, it should take you 2 to 3 minutes. So a nucleus of zinc has a charge of 4.8 times 10 to the negative 18 coulombs. The nucleus is placed in a vacuum. Calculate the electric field strength at a distance of 1.3 times 10 to the negative 10 meters from the zinc nucleus. Okay, so this is a simple application of E equal to 1 over 4 pi epsilon naught Q over R squared, which you can also write as K Q over R squared. So K is 8.99 times 10 to the 9. And this is in units of newtons meter squared over coulomb squared. Okay. Again, remember, I move all the units to the right and I keep all the numbers to the left. Okay, that's how I work. And then we have to multiply by the charge, which is 4.8 times 10 to the negative 18 coulombs. And then we have to divide by 1.3 times 10 to the negative 10 squared meter squared. Okay, and if we work all this out, we will find 2.55 times 10 to the 12 newtons per coulomb. Okay, and that's the electric field strength. Okay, question 12. A capacitor of capacitance, it's always funny when you read it, a capacitor of capacitance, 47 microfarads, plus or minus 20%, was connected to a 400 volt supply. Calculate the maximum energy that could be stored in the capacitor. All right, so since the capacitance fluctuates, we can calculate the maximum capacitance, which is going to be C max. I promise that I'm gonna try to have a better handwriting, so let me try. So C max is 47 plus 0.2, which is 20%, times 47 microfarads, and if you work this out, you find 56.4 microfarads. And then the energy stored in a capacitor is given by 1/2 CV squared, which if you plug in the numbers, you find 4.51 joules. And that's the answer. Question 13. In 1928, almost 100 years ago, by the way, one of the first LINACs was built and used to accelerate heavy ions. The ions reached the end of the LINAC with energy 1.25 MeVs and a speed of 1.1 times 10 to the 6 meters per second. The table shows some heavy ions and their masses. Okay, deduce which heavy ion was used in the LINAC. Okay, so we know from the simple kinetic energy formula, we know that kinetic energy is 1/2 mv squared. We're given the energy, which is the kinetic energy. We're given the speed, so let's solve for mass. So mass is 2 times the kinetic energy over v squared. Okay, so we have 2 times 1.25. Okay, we have to divide. So 2 times 1.25 times 10 to the 6 because it's MeVs, and then 1 eV is 1.6 times 10 to the negative 19 joules. Okay, and we divide by V squared, which is 1.1 times 10 to the 6 squared. And if we carry the calculation, we find 3.31 times 10 to the negative 25 kilograms, which you can see from the table, it's mercury. Okay, that's the closest one. Right. Question 14. I found this interesting, okay, because it's a real life application, pretty much. So, during a flight, an aeroplane was moving through the magnetic field of the Earth. At one point during the flight, the magnetic field of the Earth was at an angle of 65 degrees to the horizontal as shown. The magnetic field of the Earth has a flux density of 5.5 times 10 to the negative 5 teslas. Show that the vertical component of the magnetic flux density was about 5 times 10 to the negative 5 teslas. Okay, so this is the magnetic field, right, B. So just like every other vector, it can be analyzed into a horizontal component. Let's call it BH. And a vertical component, let's call it BV. Okay, so BV, the vertical component, is going to be B times sine of 65 degrees. And remember my silly rule, when you analyze vectors, when the component of the vector touches the angle, like B horizontal, then you take the cosine. If it doesn't touch, B vertical is not adjacent to the 65 degrees angle, so you use the sine for that one, okay? And if you do the calculation, you find 4.98 times 10 to the negative 5 teslas, which is about 5 times 10 to the negative 5 teslas. Okay, part 2. Distance xy across the wing tips was 68.4 meters. It's a large aeroplane. The aeroplane was flying at a speed of 256 meters per second. Determine the mth induced across the wing tips. Okay, so we know that the mth is minus d phi over dt. Okay, and phi is the magnetic flux. So, and it's given by BA. We don't need N here. It's not a flux linkage because we don't have a coil or something like that. Okay, so this is equal to that. Okay, and I'm gonna drop the minus sign because it doesn't matter. We don't care about that. So, and also B is gonna be B vertical, right? Because remember, you have to cut through the magnetic field lines. I mean, the horizontal component, the aeroplane does not cut through the horizontal component because it's tangent to the wings, right? So only the vertical component matters, which is constant. So I take out of that d over dt, okay? And we are left with dA over dt, okay? And what's the surface area that the aeroplane cuts through? If you picture the aeroplane moving outside the page with velocity v, then you can immediately see that as the aeroplane moves out of the page, it scans an area which is equal to bv times the velocity times the length of the wings, right? Because it creates a rectangle as it moves. I mean, I try to imagine it, okay? So I don't know how to draw it, but this is the length of the wings, right? And the aeroplane moves outwards like that, okay? With some velocity, okay? So it scans through a rectangle pretty much, okay? Which is equal to L times this side over there, right? And if we call that y, it's I hope I'm not confusing you. So this is the length L, this is the, let's call it y, and this is the area of the rectangle, pretty much, okay? So if we go to this dA over dt, we will see that we have to work with d over dt, and then the area of that rectangle is y times L, but L is constant, so we are left with dy over dt, which is nothing but L times v, which and v is the velocity of the plane as it moves in the y direction outwards of the page, okay? I hope this makes sense. If it doesn't, ask me in the comments and I will try to come up with a better explanation. But anyway, plugging numbers in, BV was 4.9 PE8 times 10 to the minus 5. The velocity is 256 meters per second. The length is 68.4. If you multiply all these, you find 0.87 volts, which is about the voltage of half an AA battery. So it can light the light bulb, probably. I don't know, something like that. All right. Now, B, the shape of the magnetic field of the Earth is shown below. An aeroplane was flying at a constant height along the equator, okay? Explain why the EMF induced across the wingtips of the aeroplane is 0, okay? So this is the plane. Let's make it like a triangle, okay? So it flies along the equator. So B is pretty much parallel to the wings, okay? So B looks like this at the equator. It's perpendicular to the equator, okay? So it's also parallel to the wings. Therefore, the aeroplane does not cut through any magnetic field lines. So there is no induced EMF for this reason. I hope this makes sense. So let's write it down. B is horizontal and along the wings of the plane. Okay, there are no vertical components. Again, I made a promise to make a better handwriting, so I'm gonna try. So no vertical components. So no change in flux. Okay, hence no EMF. And that's the answer. Let's move to question 15. In 2022, scientists using the Large Hadron Collider reported the discovery of 2 new tetraquarks. A tetraquark consists of 2 quarks and 2 antiquarks. Some scientists have suggested that the tetraquark is a combination of 2 mesons. State the structure of a meson. Okay, QQ bar, pretty much. Okay, right? So a meson consists of a quark and an antiquark. And my little comment about the tetraquark, I have a feeling that later it was discovered that it doesn't really exist or something like that. But I feel like people come up with these particles or try to stretch the statistics from some findings so they, it will appear that they found something new, so they get more funding, okay? And I'm saying this because I was for a long time a researcher, and maybe I will be a researcher again, so sometimes you hype up some things. But I don't want to sound like a crackpot, so let's actually go and, okay, let's go to my Brave browser. Okay, so tetraquark, let's see. Okay, so let's see. In particle physics, a tetraquark is an exotic meson composed of 4 valence quarks. A tetraquark state has long been suspected to be allowed by quantum chromodynamics, the modern theory of strong interactions. Okay, Okay, so they have been observed. It states it at the end. Okay, so several tetraquark candidates have been reported by particle physics experiments in the 21st century. Okay, blah, blah, blah. Okay, so they did find some, so I'm wrong. Okay, let's, after this embarrassment, let's move on to question B. And by the way, the site that you saw earlier is the website of my sister. She's a lawyer and I made it, okay, just to advertise some other things that I'm doing sometimes. So let's do B. One of the tetraquarks had a charge of plus 2e. This tetraquark consists of a combination of up-down, strange, and charm quarks or antiquarks. The table shows the charge of each quark. Determine a possible combination of quarks and antiquarks in this tetraquark. Okay, so since we need a charge of 2e, we need an up and an anti-down to get a charge of plus 1. And then to get another charge of plus 1, we need a charm and an anti-strange. Okay, so this is a possible combination. Another combination could be, let's see, is this the only combination? Let me know in the comments. I'm not going to think about it now. I'm a little bit tired because I was having severe headaches. I mean, speaking about what kept me from making videos, I couldn't. So I want to take this slowly. Okay. C. The tetraquark was produced when two protons collided. The mass of the tetraquark was 2.9 GeV over c squared. Deduce whether the mass of the tetraquark is equal to the mass of two protons. Okay, so this is straightforward pretty much. Okay, we take the mass of the proton and multiply by c squared and see what we get. So we have 1.67 times 10 to the negative 27 times 3 times 10 to the 8 squared. And if we carry on the calculation, we'll find 1.5 times 10 to the negative 10 joules, which is, if we divide by 1.6 times 10 to the negative 19 joules per eV, we find 939.38 MeV. So the mass of the proton is 939.38 MeV over c squared. So if we multiply by 2, we find 1.88 GeV over c squared, which is less than 2.9 GeV over c squared. Okay, so it's not equal to the mass of two protons. It's heavier. Okay, so D. In the LHC, the protons are accelerated to very high speeds before they collide. Explain why the protons require very high speeds to create new particles. So, because E is equal to mc squared, if protons have a large kinetic energy, some of this kinetic energy will be converted to mass. Okay, hence we need protons to have very high speeds. Right, I feel I'm going a little bit too fast today, I don't know why. So, question 16, a student, and this is the first video of 2026, guys, okay. So a student had a bucket containing some water. He swung the bucket in a vertical circle as shown. The water stayed in the bucket. State the two forces acting on the water in the bucket, okay? So both of them point downwards. So, okay, we have the weight, mg, and also the reaction from the floor N. Okay, so the two forces are gravity and floor reaction from bucket. Okay, B. The water will stay in the bucket at the top of the vertical circle if the speed of the bucket is large enough. Explain why there is a minimum speed for the water to stay in the bucket. Okay, right. There is a way to do it with just words, but I'm going to use equations as well. So let's take this instance, okay, in which the two forces point downwards. So we have N plus mg should be equal to mv squared over r, where r is this radius, I guess, okay, and v goes this way. Or maybe the other way. I don't know how the person rotates the bucket, so it doesn't matter. Okay, so the minimum N okay, the minimum N is 0. That's the case in which the bucket barely makes the circle without the water getting spilled. Okay, so in that case, mg should be lesser than or equal to mv squared over r. M cancels, so v should be larger than or equal to the square root of r times g. Okay, so the minimum speed is equal to the square root of r times g for the bucket to go around and having the water in the bucket without getting spilled. Okay. Moving on to question 17. As I said, this appeared to be a difficult test to me. Okay. So in some countries there is ice and snow in winter. Okay. I lived in one of those countries. I lived for 10 years. That was a long time in the United States, the northern states, so mostly in the Midwest, close to Chicago, where it snows heavily in the winter. Temperatures can go down to minus 20 degrees Celsius sometimes, even lower sometimes, I think. So yeah, I'm experienced with snow. So the photograph shows a child sitting inside the snow tube, sliding on ice. The friction between the snow tube and the ice is negligible. Okay, two children were in snow tubes. Child A was traveling at 2.38 meters per second. Child B was stationary. The two snow tubes collided. After the collision, child A traveled at 1.36 meters per second at an angle 33 degrees to the original direction, and child B traveled with velocity v at an angle theta to the original direction as shown. Okay, question A. Show that the angle theta was about 31 degrees. Okay, so let's go here and, okay, so the situation was that this is the situation after, but the situation before was that of child A, so with mass A, traveling with 2.38 meters per second. Okay. All right. So how can we find the angle theta? I hope I don't confuse you, but let's start with the conservation of momentum in the x direction. So in the x direction, we have the mass of child A times 2.38, which was the initial speed, should be equal to the x component of this velocity, sorry, to the x component of this momentum and the x component of that momentum. Okay. So the x component of the child A is going to be ma times 1.36 times cosine of 33 degrees, plus we have a contribution from child B with mb times v, because it's unknown, times cosine theta, which is also unknown. Okay. In the y direction, there was no momentum before because the child only moved in the x direction, okay? And we are talking about child A. So in the y direction, we have ma times 1.36 times sine of 33, okay, should be equal to mb v times sine theta, okay? Let's call this equation 1 and equation 2, and because I'm going to run out of space, I'm going to use a clean page. So if we carry on the calculations, we find v cosine theta equal to 1.86 and v sine theta is equal to 1.11. Okay, so if we divide these two, we find that tangent of theta is 0.596, which means that theta is 30.82 degrees. And while we are at it, we can find v to be equal to 2.17 meters per second, okay? So problem A says, show that the angle theta was about 31 degrees. We showed that, okay? Now B, deduce whether the collision was elastic. So we need to find 1/2 ma va squared, which is the initial kinetic energy. Okay, actually, let me erase that. Confusing. All right, so if we carry on the calculation, we find 127, actually, sorry. Let me erase this and let's write this as 2.38 squared. So this is 127.45 joules. And the kinetic energy, I'm sorry, after is 1/2 ma times 1.36 squared from child A plus 1/2 mb times the velocity of child B squared, which is 2.17. We found that. So 2.17 squared. And if we carry the calculation, we find 112.25 joules, which is less than 127.45 joules, so not elastic. Okay, question 18. Okay, I think this is still recording. So the photograph shows particle tracks in a bubble chamber. The uniform magnetic field in the bubble chamber is perpendicular to the page. It doesn't specify whether it's in or out, but I have a feeling that, okay, let me think. What did I write in my notes? I think it's out of the page, but let's see. So the tracks show the decay of a pion plus, okay, P plus. The pi plus was formed at Y over here and decayed at Z. All right, so it pretty much traveled this way, right? Okay, along this route. So it's kind of circular, and therefore we know that the velocity is tangent to this path, right? So because it's circular, we know immediately that there is a perpendicular force. There is a force that is perpendicular to V, which is the centripetal force, right? And this is caused by QVB, pretty much, right? And if we use Fleming's left-hand rule, okay, we can, so our middle finger is V, right? So middle finger, oops. I feel like I'm all over the place today. I'm sorry about that. So the middle finger is in the direction of V, and the index is in the direction of B, and then your thumb is going to show you the direction of the force. Okay, so since the force is inwards, you can place our thumb in the direction of the force, right? And we can place our, let me think. Okay, so the index finger, if we place it inwards and with the velocity to the right, then our thumb is going to be upwards. So therefore, yes, okay, I figured it out. I'm sorry, You cannot see what I'm doing. I'm using my fingers trying to figure out what's going on. So if we point our index finger out of the page and we place our middle finger along the direction of V, we will see that F is towards, it's inwards, like shown here. So we can write that, so B is out of the page because there is an F which is perpendicular to V, which is the centripetal force bending pi plus from Y to Z, right? And that's the answer. I mean, I cannot think of anything better. So again, B should be out of the page. Okay, they already say that it's perpendicular to the page, but we know that it should point outwards because if we use Fleming's left-hand rule with our index finger pointing out of the page and our middle finger pointing towards V, this V over there, we'll see that our thumb will point towards this force, which is always perpendicular to the velocity, okay, and it forces the particle to bend from Y to Z. All right, let's go to part B and part 1. So the pi plus decays to a positive muon and a second particle. The mu plus is an anti-lepton. Explain what you can identify about the second particle, okay? So mu plus has a lepton number of -1, so the second particle must have L equal to +1 and Q equal to 0, because we have a decay that goes like pi plus goes to mu plus probably a muon neutrino fits the picture, okay? Because we need to conserve charge, we have +1 before, +1 after, and we need to conserve lepton number, which is 0 before, therefore it has to be 0 after. So the only combination is for the other second lepton is to be nu minus. So a muon neutrino. I'm all over the place. I'm sorry. So I hope this makes sense. State why the second particle must move in the opposite direction to mu plus. So if we have a stationary, it doesn't have to be stationary, but let's assume it's stationary. So if we have a stationary pi plus decaying, then a mu plus will fly off in one direction. Therefore, we need to conserve momentum, because if it's stationary, it has 0 momentum before. Therefore, to balance the momentum, the muon should be in the other direction. So state why the second particle must move in the opposite direction to the mu plus. The answer is to conserve momentum. All right. So question 19, in large alpha particle scattering experiments, alpha particles were directed towards a thin gold foil in an evacuated chamber. A simplified diagram of the original apparatus used in these experiments is shown, okay? These experiments resulted in a new model for the atom. Describe the evidence and conclusions made from these experiments. Okay, so this is a long writing question. So the main observations are, so most alpha particles are not deflected. Okay, this tells you that most atoms are empty space. Okay, so the atom is mostly empty space. Then some alpha particles get deflected. Oops, again my handwriting, sorry. Deflected by small angles. This tells you that the atom is positively charged, all right? And then some alpha particles are deflected by large angles. This tells you that most of the atoms mass is in the nucleus. All right, part B, an alpha particle moves towards a gold. And by the way, for those of you who are just watching this video with past paper walkthrough, guys, I have videos discussing all these things in detail. Like these are lesson type, lecture type videos, so you can check my channel and find more in-depth analysis of what I'm writing here. Okay, so let's go to part B. An alpha particle moves towards a gold nucleus head on. Okay, the alpha particle decelerates as it moves towards the gold nucleus. The alpha particle is briefly brought to rest before traveling back along its original path. The alpha particle has a kinetic energy of 8.5 times 10 to the negative 13 joules. So show that the minimum distance between the alpha particle and the gold nucleus is about 4 times 10 to the negative 14 meters. So pretty much the kinetic energy must become equal to the electric potential energy between the alpha particle and the gold nucleus at the minimum distance. Okay, so the kinetic energy should be equal to Q times the electric potential from the gold nucleus. Okay, so 8.5 times 10 to the negative 13 joules should equal to, what's the charge of the alpha particle plus 2e, what's the electric potential of the gold nucleus, 1 over 4 pi epsilon naught times 79e, which is the charge of the gold nucleus. We take it from here, right? Okay, the proton number, right? And then we have to divide by r, and this is the r we are looking for. Okay, so if we solve for r, we find, so 1 over 4 pi epsilon naught, we can cast this into 8.99 times 10 to the 9. Okay, and if we plug everything in, we will find 4.28 times, actually, okay, let me take the step and show you what we have to plug in. So 8.99 times 10 to the 9 times 158 times 1.6 times 10 to the negative 19, which is the charge, and this should be squared, over 8.5 times 10 to the negative 13, and the result is 4.28 times 10 to the negative 14 meters, which is what they state. I mean, close. Okay, calculate the maximum force between the alpha particle and the gold nucleus. Okay, so the maximum force will be the force at the closest approach. So F is going to be K times 2E times 79E over R squared, which are this R. Okay, so if we plug everything in, we will find 19.85 newtons, which is a really, really large force. Okay, so 20 newtons is the weight. I mean, if you have a 2 kilogram mass, its weight is about 20 newtons. Okay, And this is the force experienced by subatomic particles that have a mass which is about 10 to the negative 27 kilograms. It's crazy. So that's a large force. All right. Let's go to question 20. Most mobile phones have a touch screen, which is also true for the screen I'm using right now to film this video from my iPad, okay? So the screen is connected to an array of capacitors inside the phone. When a finger touches the screen, the capacitance of part of the array changes. In the array, one capacitor has a capacitance of 22 microfarads. The capacitor charges and discharges through a resistor of resistance 1200 ohms. Question A, part 1. The potential difference across the capacitor. This capacitor was 6 volts. Show that the charge on this capacitor was about 1.3 times 10 to the negative 4 coulombs. So Q is C times V. And if we plug in numbers, we find 1.32 times 10 to the negative 4 coulombs, which is about 1.3 times 10 to the negative 4 coulombs. So we proved that. For the touch screen to be sensitive, the capacitor should discharge to 25% of its initial charge within 50 milliseconds. Okay. Deduce whether the touch screen will be sensitive. Okay, so the lifetime is given by R times C, right? Okay, and if we plug numbers in, we find that that's equal to 26.4 milliseconds. Okay, so we need to find the time needed for the capacitor to discharge to 25% of its initial charge. So we can use Q equals to Q naught e to the minus T over the lifetime, right? Is it called lifetime? No, I'm a little bit worried that I'm using the wrong wording. Let me check really quick. So unit 4. Okay. Okay, they don't name it, so fine. Okay, I'm gonna call it lifetime, whatever. Okay, let me close that. Actually, let's go back. So we were here. Okay, let's close this and continue. Okay, so we need Q over Q naught to be 1/4. Okay, so Q over Q naught should be 1/4. Okay, so let me erase this. So we pretty much need 1/4 being equal to e to the minus t over tau. Therefore, e to the t over tau is 4. And if we take the ln in both sides, we find that t is tau times ln of 4, which is 36.6 milliseconds. Okay, so 36.6 milliseconds is less than 50 milliseconds, so the screen is sensitive, right? In other words, within 36.6 milliseconds, 25% of the charge gets discharged when we touch the screen, so that's good. Okay, I don't know why it went so fast. So, sketch on the axis below how the current varies with time as the capacitor discharges. Okay, so when a capacitor discharges, we know that I is I naught e to the minus t over tau. Therefore, it's an exponential decay curve that looks like this, and it starts from I naught, and we can find I naught by using Ohm's law. So I naught is V over R. V is given as 6 volts, R is 1200 ohms. So I naught is 5 milliamps, and we can write that over there, okay? And that's the answer. Okay. Question 21. A simple diagram of an oscilloscope is shown. Electrons are released from a heated filament. The electrons are accelerated towards the anode and travel as a beam towards the screen. State the process that causes the electrons to be released from the filament. That's thermionic emission, easy. And you can see the setup there. You have a heated filament that that heats the cathode, which emits electrons. Okay. Right. Part B. A potential difference is applied across the metal plates to create an electric field between them. So these are the metal plates. Okay. Actually, let me erase all these. Okay. Let's go back. The electric field between the metal plates causes an electric force on the electrons. The potential difference across the metal plates is 120 volts. The electric field strength between the metal plates is 15,000 volts per meter. Calculate the distance between the metal plates. So E, we know that E is V over D for parallel plate capacitors or any setup in which there are parallel plates, okay? So D is V over E, and if we plug in numbers, we find 8 millimeters. All right. Okay, question 2. The electric field between the metal plates causes the electrons to accelerate with a constant vertical acceleration. Show that the vertical acceleration is 2.6 times 10 to the 15 meters per second squared. So F is equal to ma. So the force on the electrons is E times the electric field, and this should be equal to m, the mass of one electron, times the acceleration. So the acceleration is E times E over me, which is equal to 1.6 times 10 to the negative 19 times 15,000 over 9.11 times 10 to the negative 31. And if we carry on the calculations, we find 2.63 times 10 to the 15 meters per second square. All right, the beam of electrons produces a bright spot on the screen. A student measures the vertical displacement of the bright spot on the screen to be 3.4 centimeters from its undisplaced position. An electron in the beam takes 1.2 times 10 to the negative 9 seconds to travel between the metal plates. The electron takes 6.9 times 10 to the negative 9 seconds to travel from the end of the metal plates to the screen. Deduce whether an acceleration of 2.6 times 10 to the 15 meters per second squared will produce a vertical displacement of 3.4 centimeters. Okay, so this is a complicated problem. So let me show you the setup. So these are the parallel plates. Okay, so let's assume the electron is in the middle. Okay, so it starts like this and it gets displaced like this. Okay, so this was the initial trajectory, but it gets deflected because of these two green electric plates. Okay, so we know that the electron spends 1.2 times 10 to the negative 9 seconds in the plates, and it spends 6.9 times 10 to the negative 9 seconds outside the plates, okay? And the student claims that this y is equal to 3.4 centimeters. And we're going to put a question mark because you don't know if it's equal to 3.4 centimeters. Okay, so first of all, we have to work with Suvat equations. Again, I remind you that even though you're taking Unit 4 and Unit 5 and Unit 6 and so on, it's good to do a refresher of Unit 1, 2, and 3, and especially the Suvat equations, things like the second Newton law, etc. When you're tested on physics, it is usually assumed that you know the physics that came before the physics that you are taking, okay? So AS level physics is required knowledge for this test. Okay, so a good first step is to find the velocity in the y direction inside the plates. Okay, so inside the plates, Vy is u plus ay times t, and ay is the acceleration we found earlier. Okay, since the electrons had no acceleration in the y direction before entering the plates, the initial velocity is 0. Okay, in the u direction. So, and we know that the time spent inside the plates is 1.2 times 10 to the negative 9. So if we plug in 2.63 times 10 to the 15 times 1.2 times 10 to the negative 9, we know that Vy is 3.16 times 10 to the 6 meters per second. Okay. So that's the final velocity in the y direction when the electrons reach this place, the outside of the plates. Okay. So while inside the plates, they get deflected, right? So you can use SWOT equations to find how much they got deflected inside the metallic plates, okay? So during their time in the plates, they get deflected by y equal to u times t, but there is no initial velocity in the y direction, okay, plus 1/2 ay times t squared, and we will use the same t. So t is 1.2 times 10 to the negative 9 seconds, and ay is 2.63 times 10 to the 15. And if we use these two, we find that the vertical displacement right after they exit the plates is 1.89 millimeters, which is good because remember that the distance between the plates is 8 millimeters, okay? So if the deflection was like 5 millimeters, we will know that the electrons actually touch the upper part of the metal plates. I hope this makes sense. If it doesn't, ask me in the questions, in the comments, and I will respond. So after the electrons, after the electrons exit the plates, ay is now 0. But they have some initial velocity, okay? But let's call it uy is 3.16 times 10 to the 6 meters per second, okay? So they will get deflected. So y is again uy times t plus 1/2 ay t squared, but ay is now 0 outside the plates, okay? And Vy is 3.16, so 3.16 times 10 to the 6 times t, and now the t is 6.9 times 10 to the, so 6.9 times 10 to the negative 9 seconds, right? And if we carry on the calculations, we find 19.27 millimeters. So y total is 19.27 plus 1.89, which is 21.16 millimeters, which is less, which is actually actually 2.12 centimeters, which is less than 3.4 centimeters. So the student is wrong. Which is often the case with students. Okay, I'm not that type of person that makes fun on students. I'm sorry. Okay, so it was a joke. All right, so let's move to question 22, which is the last question in this very long test. Okay, this was a difficult test. Okay, so a cylindrical copper rod PQ is placed on a pair of copper rails. Okay, the rails are connected to a battery and a switch. The rod and rails are in a uniform magnetic field, which is directed into the page as shown. When the switch is closed, the force acts on the rod and it begins to move along the rails. Explain which direction the rod moves along the rails. Okay, so F is BIL, and if we use Fleming's left-hand rule for this scenario, now we will have to adjust a little bit. So B is still our index finger, I is our middle finger, and F is the thumb. Okay, so I from the battery goes like this. Okay, so I points downwards. Okay, and if we put our index finger into the page and our middle finger pointing down, we will see that F is to the right. Okay, so from Fleming's left-hand rule, force is to the right. Right. B. Okay, the rod accelerates uniformly from rest along the rails. After the rod has traveled 6.5 times 10 to the negative 2 meters, it has a speed of 3.5 times 10 to the negative 2 meters per second. Calculate the magnetic flux density of the magnetic field. Okay. Again, we have to use Suvat equation. So V squared is U squared plus 2AS, right? But U squared is 0, the initial velocity is 0, so you can find the acceleration from this equation. So the acceleration is V squared over 2S. And for V, we will use this. And for S, it's the distance traveled. So if we plug in numbers, we find 9.42 times 10 to the negative 3 meters per second squared, right? And now from F equals ma, we know that the force is B times I times L, and this is M times A. So we have to solve for B because this is what we are looking to find. So B is ma over IL. So the mass is 1.5 times 10 to the negative 2 kilograms. The acceleration is what we found earlier, and I is 0.32 amperes, and the length of the rod is given. So if we plug everything in, we find 5.88 times 10 to the negative 3 Teslas. Okay. And last but not least, friction is negligible as the rod moves along the rails. If the rails, so the friction is negligible, okay, that's a key. If the rails are long enough, the rod will eventually reach a constant velocity. Explain why. Okay, for anything to reach terminal velocity, we need the force acting on a body to go to 0, okay? So somehow this has to happen. So explain why. You should consider the effect of a conductor moving through a magnetic field. Okay, so we immediately have to think of Ampere's law for mth. So E is minus d phi over dt. We have no turns or coils or stuff like that, so we don't need the n. So we will have minus b dA over dt in this scenario, and you will see where I'm going with this. So if we take the rod, okay, let's say that the rod moved over here, then we know that the rod cut through magnetic field lines, right? And this is the area it cuts through, and the area is given by the length times this distance, let's call it x, L times x. So if we go to this law over here, we will find, oops, I don't know what happened. We will find minus BL dx over dt, which is nothing more than V, so BLV. Okay, so let me use a clean page so you can say things like this. the motion of the rod. So what I'm trying to say is that an EMF is generated across the rod pretty much, okay? So the motion of the rod, okay, cuts through B, okay? Hence, there is d phi over dt, which is not zero, generating an EMF. All right, so because we have a closed loop, a current is, generated. I think it's running out of battery, okay? Is generated such that it counteracts the reason that created it. Which is Lenz's law. Lenz's law. Okay. Thus the current, the generated current, okay, will be opposite to the original current. Okay. Eventually, I total will be 0, okay? Hence, the force will be 0, and A will be 0, and the terminal speed will be reached. And that's the answer, okay? This was a long test. Actually, let me open the mark scheme. I'm a little bit insecure now for some reason. Okay, the mark scheme is over here. This was the last question. Let me see what they say here. So question 22, part C. As the rod moves through the field, there is a change of flux, which induces an EMF. The EMF acts to oppose the change that caused it. Okay, induced EMF acts to oppose battery EMF. Okay, or when the current is 0, resultant force is 0. Okay, so that's a correct answer. All right. Okay. So this was Unit 4 from October 2025. Again, there is a Unit 4A available. I don't know how it's different from this Unit 4. I haven't checked yet. If it's very different, I might solve that one too. Expect more videos to come out soon, I hope. I'm gonna walk you through Unit 5 from October 2025, probably, and Unit 6, and maybe Unit 1 and Unit 2 and Unit 3. We'll see. I still need to finish the Unit 1 material. But anyway, hopefully I will keep uploading these videos. Please like and subscribe, guys, and let me know what you think about these videos. So see you in the next one.